Welcome students. In the previous lecture we have studied how exactly to obtain integration. So for example, take this particular question which we did in the previous class. In this case it is merely involves the application of simplification and direct application of the formulae which we have studied. So there aren't any other extra things that is being done in this particular question. In fact, all of the questions that were done in the previous lecture were mere application of the formulae in integration. But in today's class we will obtain, or in other words we will understand the technique of substitution. Now when exactly this technique is used? Now whenever you are given a problem which cannot be simplified or which cannot be appended using concepts in algebra, then we would resort to using this technique called a substitution. This is one of the powerful techniques available in integration. So I will start off by handling simple questions, and then gradually I will move up the ladder so that the intensity of the question is very much challenging and prepares you for all competitive examinations as well as for graduate schools. So having mentioned that, let me just start off with this particular question. Say you are expected to integrate sine of x raised to the power of 3 times 3x squared dx. Now there is no way we can use some manipulations available in algebra to handle this, at least from the beginner's perspective. Of course there are varied other techniques available in calculus, but in this case we will just use substitution method. So foremost what I would do is I will start off with this keyword. You can say it is a keyword let. This is important. You will have to place this let before you could start your substitution technique. So what I'm going to do is I'm going to say let x raised to the power of 3 be equal to some variable. So left hand side is a variable, right hand side is a variable. The only difference is that the left side variable that you are seeing, x cubed, is actually part of the question. So it is appearing over here. So that is mandatory. Now what I'm going to do is I'm going to be differentiating both sides. We get, maybe I will just take this off. This is going to give me 3 times x squared times dx, and this is going to give me dt. So this is what you will have to remember. Now you can clearly see 3 times x squared dx is featured over here. So hence the original system integral sine of x to the power of 3 times x squared dx is now rewritten as integral. In place of x cubed, I'm going to place t. In place of 3 times x squared dx, I'm going to place dt. So this is nothing but integral sine t dt. What is integral sine t dt? It is going to be negative cos t. But you don't have to place the arbitrary constant c over here because it is still not in the original variable x. So now t is actually x cubed. So this is nothing but negative sine cos of x raised to the power of 3 positive c. So this is the final solution for the question. Now let's do another question so that we will be able to get a better grip, because the more the question we do, the better we are. So now question number 2. We are given to integrate integral e raised to the power of tan inverse of x over 1 positive x squared. Dx should be there. This operator should be there. Without the operator, this is considered incorrect. Without this differential operator, this entire question is considered incorrect. So you will have to place this differential operator. So the question is, how are we going to do this? So I'm going to start off with stating let tan inverse of x be equal to t. So differentiating both sides, that's the best word to use. Differentiating both sides, we get. So what do you get? What is the differentiation of tan inverse of x? Differentiation of tan inverse of x would give us 1 over 1 positive x squared times the differential operator dx. The differentiation of t is going to be dt. So this entire question, hence you can state, hence this entire thing is now equal to integral. In place of tan inverse of x, substitute t in the place of dx over 1 positive x squared. What are we going to do? In the place of dx over 1 positive x squared, we have to substitute dt. So this is actually over 1. Since I've already drawn a byline, I just want to place 1. So in the place, as I mentioned to you, dx over 1 positive x squared, I substitute dt. Now what is this? This is nothing but integral e raised to the power of t times dt. And what is this? This is nothing but e raised to the power of t. But what is t? T is nothing but tan inverse of x, positive arbitrary constancy. So that is the solution for this question. So you will have to revert back to the original variable x. If you do not revert it, then one of the two things will either occur. That will be, you would not be able to make the correct choice because your choice is not going to be featured there in the multiple choice if this reversion is not achieved. Number two is, if in case it is subjective type questions, you would not be able to score complete solution. In other words, complete score for that particular solution. So in either cases, you are at a disadvantage. So make sure to reach this point. It is imperative that you get this. Okay, so let's move on. Question 2. So it's actually question 3. So you are given to integrate integral. Let me take this 2 times x cos of x squared negative 5 times dx. So how are we going to integrate this? This is going to be, foremost, as I mentioned to you, let x squared negative 5 be equal to t, differentiating both sides. We get, so what do we get when you differentiate both sides? Differential of x squared is 2 times x times differential operator. Differentiation of constant is 0. Differentiation of t is going to be dt. So we get 2x and a dx. So if you want to rewrite this, this is actually going to be cos of x squared negative 5 times 2x dx, which is equal to integral cos of x squared negative 5 is going to be t, 2x dx is going to be dt. This is nothing but cos t dt, which is going to be sin t. But what is t? T is x squared negative 5 with the constant c. So that is a good place for us to draw the line. So that's a good question. So now let us move on to some other questions. Say I've got this question to integrate root of, say, a squared negative x squared times dx. How are we going to integrate this? This is a challenging integration, and in cases like this we will have to resort to trigonometric substitution. So this is what is called as trigonometric substitution. Okay, in trigonometric substitution, so how different is this substitution from the one that we are going to study? In this substitution, it is a direct substitution using algebraic techniques. That's it. There aren't anything else other than that. It's because if you were to notice, we are only using t, and t, even in the previous case, we just used t. So just a variable. So you can either call it as a variable substitution or simple substitution. Now in this case, it's going to be trigonometric. So what I'm going to do is I'm going to state, or in other words, I'm going to take, let x be equal to, I need to cater to this constant a times, we will always start with sin theta. The substitution that we will use for questions like this is x is equal to, depending upon the constant that you see, we will use that substitution, that value over here. Now differentiating both sides, what do we get? Differentiating both sides, we get, what is the differentiation of x? Dx. What's the differentiation of a times sin theta? It's going to be a times cos theta times d theta. So this is, you can state, hence this becomes equal to, this is equal to integral root of a squared. In place of x, it's going to be a sin theta. So in other words, this is going to become a squared sin squared theta, and then in place of dx, so this is going to become a times cos theta d theta, right? So if you were to rewrite this, it's going to be integral root of, I'm taking a squared out, so it's going to be 1 negative sine square theta, parenthesis, draw the square root, and then outside the square root is going to be a times cos theta d theta. So this is equal to integral, I can bring a squared out, so it will become a, this is going to be root of 1 negative sine square theta is going to be cos square theta. You got an a here, so that a can be multiplied, giving us a squared. So you get a cos theta d theta, which is nothing but a squared. Root of cos square theta is cos theta. Cos theta can be multiplied. So I'm going to get cos square theta d theta. But this can be rewritten with the formula. What is the formula? Let me just use the space here. See, 1 positive cos 2 theta divided by 2 is equal to cos square theta. So in place of cos square theta, I'm going to use this formula. So this is equal to a squared of 1 positive cos 2 theta divided by 2 times d theta. Now I can split this. I can take a squared out. I can take 2 out. So this is going to be a huge parenthesis over here. Integral d theta times 1 positive integral cos 2 theta times d theta. So close the parenthesis. So this is what we have got. So let me use this space over here. So what happens here? This is equal to a squared over 2 parenthesis integral d theta is theta, integration of cos 2 theta is going to be sin 2 theta. The coefficient of theta is 2, so we divide it. So this is what we have got. But now this is not yet complete. We will have to revert it back for theta. So for that, so let me use this space over here. Now we have taken x to be equal to a times sin theta. So push this a down. This is x over a is equal to sin theta. We need theta, so push this sign to the other side. So sin inverse of x over a is equal to theta. But what did we get? Our solution is, we got this a squared over 2 theta positive sin 2 theta over 2. So if I were to substitute the value of theta, this is a squared over 2, this is sin inverse of x over a positive sin 2 times of sin inverse of x over a divided by 2. So this is what positive arbitrary constancy. So this is what we have got. Now in fact, if you are not happy with sin 2 theta, you can always rewrite sin 2 theta. You can always rewrite sin 2 theta, because some may not be liking sin 2 theta's appearance. So in that case, or if this solution is not present, probably you can revert this into the equivalence of the relationship that we know, because sin 2 theta is nothing but 2 times sin theta cos theta, but this is divided by 2, so you can get rid of this 2. So in that case, sin of theta is nothing but sin inverse of x over a. So I substitute sin inverse of x over a, that is fine for the first component, times cos of sin inverse of x over a. This is for the second component, right? So in fact, sin inverse and sin can be cancelled. So this is going to be x over a times cos of sin inverse of x over a. So in place of sin 2 theta over 2, we can substitute this. And if you substitute this would be more attractive than this, right? I want to show you one more alternative. Still, if you are not happy with this, what we can do is, I would like to use this space here. Now we have this cos theta, right? So we have actually replaced, or we have actually obtained x over a cos theta. This is what we have got from over here, because in this case, if you were to, I'm not going to substitute this, I'm just going to retain this as theta. So there is no substitution, it is just retained as theta. So in this case, we are reducing it to x over a, that's fine. But cos theta, we can always write cos theta as root of 1 negative sine square theta. So this is going to be equal to x over a square root of, but sine theta is what? Sine theta is actually x over a. So you can substitute that. So this is going to be 1 negative x over a the whole square. That's going to be x squared and a squared. So the root is actually flowing, covering everything. So this can be rewritten as x over a root of, I can take the LCM, that would give me a squared negative x squared divided by a squared. If I were to apply this root for a squared, a would be the outcome. So this is equal to x over a squared root of a squared negative x squared. So if in case they are asking us to produce everything in x alone, then the result is going to be a squared over 2, and the first component is going to be sine inverse of x over a. Of course, for this, in this case of this sine 2 theta, which we have just written sine 2 theta, this is going to be, so let me just place the first component, sine inverse of x over a positive x over a squared root of a squared negative x squared, positive arbitrary constancy. So this is the third way we can represent the given solution. Students, we are expected to integrate integral cos of ln x over x times dx. So foremost, I'm going to state, let ln x be equal to t, and then differentiating both sides, we get differential of ln x is going to be 1 over x times differential operator dx, differentiation of t is going to be dt. So this can hence be rewritten as integral cos of, in place of ln x I'm going to substitute t, in place of dx over x I'm going to substitute dt. Of course, since I placed the byline, I will place a 1 there, so this can be rewritten as integral cos t dt. But what is integration of cos t? It is going to be sin t. But what is t? T is nothing but ln of x. And of course, we need to add the arbitrary constant c. So this is the solution to the question. So we move on to the next question, students. So we are expected to integrate integral x raised to the power of 3 over 1 positive x raised to the power of 8 times dx. Students, before we could integrate this, we will have to rewrite this as integral x raised to the power of 3. The denominator is x raised to the power of 8. So I'm going to use some concepts in algebra and rewrite this as x raised to the power of 4 raised to the power of 2. So this is the way I'm going to rewrite x power 8. Because if from algebra we know that x raised or a raised to the power of m times n can be rewritten as a raised to the power of m times n, or we can rewrite this as a raised to the power of n times m. So these are all possible ways from the law of exponents. So what I'm going to do is, I am going to be making this following substitution. I'm going to state, let x raised to the power of 4 be equal to some t. Now differentiating both sides, we get, so what do we get when we differentiate x raised to the power of 4? This is going to be 4 times x raised to the power of 3 times differential operator is equal to dx. There aren't any 4 over here, so I'm going to push the 4 down. So this is going to be x raised to the power of 3 times dx is equal to dt over 4. So this is for the substitution part. So hence this entire thing can be rewritten as, of course there should be the differential operator dx. In place of x raised to the power of 4, I'm going to substitute t. So you have a degree 2 here, so that's going to be square, t square. In place of x raised to the power of 3 times dx, I'm going to be substituting dt over 4. So this is dt, 4 is a constant, so I can place it over here. Now this is our famous tan inverse of x formula. So I can rewrite this as 1 over 4 times tan inverse of t. So this is rewritten as 1 over 4 tan inverse of Now what is t? T is nothing but x raised to the power of 4. Along with that, we need to place the arbitrary constant c. So this is our final solution. 1 over 4 times tan inverse of x raised to the power of 4 positive c. So that's a good place for us to draw the red line. Students, we are expected to integrate ln of x positive square root of 1 positive x squared over root of 1 positive x squared. Now what I'm going to do is I'm going to make the following substitution. Let ln of x positive root of 1 positive x squared be equal to t. Then differentiating both sides, we get, so differential of ln is going to be 1 over x positive root of 1 positive x squared times differentiation of this entire quantity. So differentiation of x is 1. Now we need to differentiate, let me just show that to you over here. We need to differentiate root of 1 positive x squared. Now this is nothing but 1 positive x squared raised to the power of half. So if you were to differentiate this, this is going to be 1 over 2 times 1 positive x squared raised to the power of half negative 1 times differentiation of 1 is 0. Differentiation of x squared is going to be 2x. So 2 can be cancelled. This is going to be x times 1 positive x squared raised to the power of half negative 1 will give you negative half, which can be rewritten as x over root of 1 positive x squared. So this is just for your understanding. Okay, so that is exactly what I need to write here. So differentiation of this entire component would give me x over root of 1 positive x squared times the differential operator dx. Differentiation of t is going to be dt. Now I can simplify this using the Lcm technique. So this is going to be, let me rewrite it over here. This is equal to 1 over x positive root of 1 positive x squared times this simplification is going to be root of 1 positive x squared positive x divided by root of 1 positive x squared times dx is equal to dt. So clearly we can see that x positive root of 1 positive x squared can be cancelled with this. So that in turn would give me dx over root of 1 positive x squared is equal to dt. So this is a beautiful representation for our question. So this is now going to be equal to integral. In place of ln of x positive root of 1 positive x squared, I am going to substitute t. In place of dx over root of 1 positive x squared, I am going to substitute dt. So this is going to be the situation. If I were to integrate this, this is going to be t squared over 2, but t is ln of x positive root of 1 positive x squared, that is going to be my t. It has to be raised to the power of 2 and divided by 2 with the arbitrary constant c. So this is our solution, and it's a good place for us to draw the red line. Students, we are expected to integrate integral x raised to the power of 2 times tan inverse of x raised to the power of 3 over 1 positive x raised to the power of 6 times dx. Now this is a classic illustration for multiple substitution. So foremost what I'm going to do is I'm going to take this, let x cube be equal to t, differentiating both sides, we get differential of x raised to the power of 3 is 3 times x squared times dx. Differential of t is dt. So this can be rewritten as integral. Now I'm going to be, in fact I don't have a 3 there, so x squared dx is going to be equal to dt over 3. So in other words, what I'm doing is I'm going to rewrite this first as tan inverse of x raised to the power of 3 times x squared times dx over 1 positive x raised to the power of 6. Now this is equal to integral tan inverse of, in place of x cubed is going to be t, in place of x squared dx is going to be dt over 3. So this is going to be dt. I want to place this 3 there, and one positive x raised to the power of 6 can be written as 1 positive x cubed raised to the power of 2. This is going to be 1 positive x cubed is t, so it's going to be t squared, right? So that's exactly what I'm going to substitute here, 1 positive t squared. So if I were to rewrite this, this is going to be 1 over 3 integral tan inverse of t over 1 positive t squared times dt. Now this is the first substitution, right? Now I need to start on second substitution. Now I'm going to take, let tan inverse of t be equal to sum p, and I differentiate. So differentiating both sides, we get, so differential of tan inverse of t is what? 1 over 1 positive t squared times differentiation of t dt. Differentiation of p is going to be dp. So this is equal to 1 over 3 times integral tan inverse of t is p, dt over 1 positive t squared is going to be dp. Differentiation, or I should say integration of this would give me p squared over 2. I can rewrite this as p squared over 6, but my p is what? Tan inverse of t. So this is going to be tan inverse of t raised to the power of 2. There is a 6 here, I place the 6. But my t is what? My t is x cubed. So I need to get the original variable back. Let me box this off. So it's going to be 1 over 6 tan inverse of x cubed raised to the power of 2. So this has to be added with the arbitrary constant c. So just to be a little bit more appearable, I'm going to rewrite this as 1 over 6 tan inverse of x cubed raised to the power of 2 positive arbitrary constant c. So that's a good place for us to draw the red line. Now, sometimes certain questions, even though we are using two substitutions, they might even be resolved with a single substitution. So I'm going to show you the alita for this question, but not all the times it would be possible. But apparently for this question, it is possible to achieve the solution with a single substitution. So we are given integral x squared tan inverse of x to the power of 3 over 1 positive x raised to the power of 6. Of course, the differential operator has to be placed there. Now what I'm going to do is, I'm going to take, let tan inverse of x cubed be equal to, say, t. Now differentiating both sides, we get, so differentiation of tan inverse of t is what? It's going to be 1 over 1 positive t squared. So in place of t, I get x to the power of 3, and that has to be taken to the power of 2 times differentiation of x cubed. That's going to be 3 times x squared dx. On the right we got dt. But as I mentioned to you, there aren't any 3 there. So I'm going to rewrite this as x squared dx over 1 positive x raised to the power of 6 is equal to dt over 3. So this is going to be my substitution. So this can be rewritten as, I'm going to rewrite this as integral tan inverse of x cubed over 1 positive x raised to the power of 6 times x cubed times dx. Now in place of tan inverse of x cubed, I can substitute t, and in place of x cubed dx, in other words, this is not x cubed, this is x squared. So in place of x squared dx over 1 positive x raised to the power of 6, I can substitute dt over 3. So this is going to be dt over 3. I can rewrite this as 1 over 3 times integral t dt. If I were to integrate t, it's going to be t squared over 2, and this can be rewritten as 1 over 6. T is tan inverse of x cubed. Place that. Apparently there is a 2 there, and this has to be added with an arbitrary constant c. So we get the same result. If you were to compare the result 1 and result 2, we get the same result. So hence that's a good place for us to draw the red line. So having mentioned or having shown you this technique, I should also tell you that not always that questions can be avoided from applying to substitution whenever it is required for them. So we'll move on to the next question, students. Students, we are given this question. We are expected to integrate integral of tan of root of x times secant squared of root x over root of x times dx. So foremost, I will wish to make the following substitution. Let tan of root of x be equal to t. Differentiating both sides, we get, so differentiation of tan x would give us secant squared x. So in this case, it's going to be secant squared of root x times differentiation of root x. So let me show you this. If you expected to differentiate root of x, this is nothing but d of x raised to the power of 1 over 2, which is 1 over 2 times x raised to the power of 1 over 2 negative 1, which is equal to 1 over 2 times x raised to the power of negative 1 over 2, which is going to be 1 over 2 times root of x. So this is exactly what I'm going to place here, because we need to place the differentiation of root of x. So that's going to be 1 over 2 times root of x times dx is equal to dt. Differential of t is going to be dt. So now we need to do some arrangements. So what are those? So if you see this question has got tan root of x, that's fine. This has got secant squared root of x over root of x times dx, but there isn't any 2 there, so we need to push the 2 there. So this is going to be secant squared root of x divided by root of x dx is equal to 2 times dt. So we will be using this substitution. So this is going to be this, and this is going to be this. So this is equal to integral, in place of tan root of x, we are going to have t. In place of this entire thing is going to be 2 times dt. I'll place the 2 here, and I'll place dt here. So integrating this would give me t squared over 2. 2 can be cancelled, but my t is tan root of x. This has to be raised to the power of 2, and plus an arbitrary constant c. Of course, you can rewrite this as tan squared root of x plus c. So this is a good place for us to draw the red line, students. Now, students, this is a very important integration, integral of tan x dx. Now, we can rewrite tan x as sin x or cos x with the differential operator dx. Now what I'm going to do is I'm going to state, or I'm going to take, let cos x b is equal to t. So differentiating both sides, we get differential of sin x is going, differential of cos x is going to be negative sin x along with the differential operator. Differential of t is going to be dt. So this is sin x dx is equal to negative dt. So I can rewrite this sin x dx as dt with a negative sign outside, and cos x is t. So if I were to integrate this, this is going to give me ln t, but my t is cos x, and arbitrary constant has to be added. Now this is one result which you have to know. So integral of tan x is negative ln cos x plus c, or we know that from logarithms a times ln b is equal to ln of b over a, right? So this is actually negative ln of t can be rewritten as ln of t. Of course, this negative is actually negative 1, so I'm going to rewrite it like this, and I can rewrite this again as ln of t raised to the power of negative 1, which can be rewritten as ln of 1 over t, which is going to be ln of 1 over cos x, which is going to be 1 over cos x is secant x, so it's going to be ln of secant x, positive arbitrary constant c. So this is the second result which you will have to know. So there are two representations. So similarly, you can prove that integral cot x dx is equal to, now this is negative ln of cos x, right? But for integral of cot x, it's going to be ln of sin x, positive c. So that's the important result that you will have to know. So along with these two results, you got the next result, which is integral of secant x. So integral of secant x dx, we are going to see that the result is ln of secant x positive tan x positive c, or it is ln of modulus tan of pi over 4 positive x over 2 positive c. So I'm going to show you how this result is obtained. So this is the modulus sign. So let's get this result out of the way. Students, foremost, what I'm going to do is, let us start off by considering integral secant x dx, and I'm going to rewrite this as secant x. I'm going to multiply the numerator by secant x positive tan x, and I'm going to divide it by the same quantity. So in this way, I'm not making any changes at all, because secant x plus positive tan x can be cancelled with the 1 in the denominator, so there isn't any extra changes. Now I would like to distribute secant x, so that would be secant x times secant x, so it's going to be secant squared x positive secant x times tan x, it's going to be secant x tan x times dx divided by secant x positive tan x. Now let me make the substitution. Let secant x positive tan x be equal to t. Differentiating both sides, we get differential of secant x is secant x tan x. Differentiation of tan x is secant squared x. We need to place the differential operator, and that is equal to dt. Now clearly you get secant squared x, secant x tan x with dx. So this is rewritten as integral dt divided by secant x positive tan x is t. So this is going to be ln of t, which is nothing but ln of, in place of t I need to substitute secant x positive tan x, positive arbitrary constant c. So this is the first outcome. Now there is another equivalence that we have, so we need to obtain that equivalence. So how do we do that? So we're going to start from here. So this is equal to ln of secant x is 1 over cos x, and tan x is sin x over cos x. I'm not going to place the arbitrary constant c as yet, okay? But if you think you need to place it, you can place it. Okay, anyway, I'll go along with placing the arbitrary constant. So this is rewritten as ln of, I'm taking LCM as cos x, and that would give me 1 positive sin x. Now this is equal to 1, I can rewrite 1 as sin squared x over 2 positive cos squared x over 2 positive. Why do I write it like this? Because I want to replace sin x with the 2 sin x formula, but this has got only x, so this is going to be rewritten as 2 times sin x over 2 times cos x over 2, right? So this is divided by, now cos x we can actually utilize cos 2 theta formula, which in this case is going to be cos squared x over 2 negative sine squared x over 2. So you have everything inside the logarithm. So this is equal to ln of, I can rewrite this as, probably what I'll do, instead of starting with sin x positive cos x, I am going to rewrite this as cos x over 2 positive sin x over 2 the whole squared, and this is inside this ln, right? Because cos x over 2 positive sin x over 2 raised to the power of 2 would give me this. Now this is divided by cos squared x over 2 negative sin squared x over 2. Now is it okay if I write this as cos x over 2 negative sin x over 2 times cos x over 2 positive sin x over 2? Can I write this? Because this is the form a squared negative b squared. So clearly what happens here, one of the cos x over 2 positive sin x over 2 can be cancelled with cos x over 2 positive sin x over 2. So this is going to be equal to ln of cos x over 2 negative sin x over 2 divided by, in fact it's positive, divided by cos x over 2 negative sin x over 2, right? So from here, of course, there you can continue placing the arbitrary constant. Now this is equal to, what I wish to do is, I would like to take cos x over 2 out. So if I were to take cos x over 2 out, it's going to be 1 positive sin x over 2 divided by cos x over 2. The entire component is divided by cos x over 2. I'm taking cos x over 2 out. So this is going to be 1 negative sin x over 2 divided by cos x over 2. So this is what we have got. Now clearly cos x over 2 can be cancelled, and I can rewrite this as ln of 1 positive sin x over 2 over cos x over 2. This is going to be tan x over 2 divided by 1 negative tan x over 2. Now this is actually a formula, right? Now what is this formula? Now if I were to use tan of a positive b, I would get tan a plus tan b divided by 1 negative tan a tan b, right? This is the formula. Let me place the c there. We know that. Now if I take a is equal to pi over 4, so this is tan of pi over 4 and b is x over 2, I would get tan pi over 4 plus tan x over 2 divided by 1 negative tan pi over 4 tan x over 2. Tan pi over 4 is 1 positive tan x over 2 divided by 1 negative tan x over 2, right? So this is for your understanding. So this entire component can be rewritten as ln of the formula tan of pi over 4 plus x over 2 plus arbitrary constant c, and this is a good place for us to draw the line. But since we are using tan, I would place a modulus sign, and this is a good place for us to draw the line. Now students, let us see what happens when we integrate cosecant x dx. Now I'm going to rewrite this as integral cosecant x times, I'm going to multiply the numerator by cosecant x negative cot x, and I'm going to divide by cosecant x negative cot x times dx. Now I'm going to distribute cosecant x, so this is going to give me cosecant squared x negative cosecant x cot x times dx divided by cosecant x negative cot x. Now let cosecant x negative cot x be equal to some t. Differentiating both sides, we get differential of cosecant x is negative cosecant x times cot x. Differentiation of cot x is negative cosecant squared x, so that's going to be positive there. So we need to place the differential operator, and this is equal to dt, right? So I need to rewrite this, or in other words, I'm going to start with cosecant squared x negative cosecant x cot x times dx is equal to dt, so that I can make the substitution here. So this is going to give me dt, cosecant x negative cot, that's going to be t. If I were to integrate, this is going to be ln of t, and this is going to be ln of cosecant x negative cot x, positive arbitrary constancy. So this is a very important result. Now there is another result also for cosecant x, integration of cosecant x. So that's exactly what we are going to see. So let us see that integration. So from here we are starting, so this is equal to ln of, in place of cosecant x, I'm going to substitute 1 over sin x. In place of cot x, it's going to be cos x over sin x. Now I can rewrite this as ln of, taking LCM as sin x. This is going to be 1 negative cos x positive. Of course, there's an arbitrary constant that will continue. Now we got a formula, 1 negative cos 2x over 2 is equal to sin squared x, but we don't have 2x here, we got only x, so this can be rewritten as ln of 2 times sin squared x over 2. Similarly, sin x can be rewritten as 2 times sin x over 2 times cos x over 2. Now the 2 that you see here can be cancelled, and sin x and a sin x can be cancelled, giving me ln of sin x over 2 divided by cos x over 2, which can be rewritten as ln of tan x over 2 positive arbitrary constancy. So this is also a very important result, that is involving cosecant x. So 2 results we have got. So we'll move on to the next question, students. Students, we have given a beautiful question. We are expected to integrate secant raised to the power of 2 over 3 x times cosecant raised to the power of 4 over 3 times x. Now we know that secant x is 1 over cos x and cosecant x is 1 over sin x. So we are going to be utilizing these two equivalents over here. So this can be rewritten as integral 1, in fact I can just say dx over, in place of secant raised to the power of 2 over 3 times x, I'm going to write it as cos raised to the power of 2 over 3 times x. In place of cosecant, it's going to be sine raised to the power of 4 over 3 times x. Now what I wish to do is, I would like to divide this by cos raised to the power of 4 over 3 times x and multiply it with cos raised to the power of 4 over 3 times x. So I'm not making any changes, but this will impact even though it is not visible, the impact will be in a greater level, so as that we can easily obtain the solution. Now, we can use the law of indices. A raised to the power of m times a raised to the power of n is a raised to the power of m positive n. So we got here, so these are all working, we got here cos raised to the power of 2 over 3 times x times cos raised to the power of 4 over 3 times x. Actually, I am connecting this with this. So this is equal to cos raised to the power of 2 over 3 positive 4 over 3, which is equal to cos of 6 over 3, which is equal to cos squared x, right? So that's exactly what I'm going to write. So this is equal to integral dx over, this is cos squared x, this is tan, in fact I can write it as tan x raised to the power of 4 over 3, right? I can always do that. Now 1 over cos x is secant x, so this is equal to integral secant squared x dx divided by tan x raised to the power of 4 over 3. Now I am going to make the substitution. Let tan x be equal to t, differentiation or differentiating both sides, we get differentiation of tan x is secant squared x dx, differentiation of t is dt. So this is going to be rewritten as integral. In place of secant squared x dx, I am going to substitute dt. In place of tan x is going to be t, but there is a 4 over 3 there. If I were to move this to the numerator, this is going to be t raised to the power of negative 4 over 3 times dt. Now, since we know integral x raised to the power of n times dx is x raised to the power of n positive 1 over n positive 1 positive c, I'm going to be using this over here, and that would give me t raised to the power of negative 4 over 3 positive 1 over negative 4 over 3 positive 1, which can be rewritten as, taking LCM, I get negative 1 over 3 over negative 1 over 3, which can be flipped and rewritten as 3 over, of course I will have a negative sign, I can push this down, 1 over 3, right? So this is equal to negative 3 over, my t is tan x, so this is going to be tan x raised to the power of 1 over 3, or you can rewrite it as negative 3 over tan 1 over 3, tan raised to the power of 1 over 3 times x, positive arbitrary constant c, and this is a good place for us to draw the red line. Of course, you can rewrite this as negative 3 times. You can take it to the numerator, so that's going to be tan raised to the power of negative 1 over 3 x positive c. So you can either stop here or you can stop here depending on the requirement, but make sure that these two results are obtained, or in other words you are able to achieve these two variations. Students, we are given this question. We are expected to integrate integral x times square root of 2 times x squared negative 1 negative sine 2 times x squared negative 1 over 2 times sine x squared negative 1 positive sine 2 times x squared negative 1 with the differential operator. Now we got x outside and we got x squared negative 1 inside. So what I'm going to do is I'm going to take the substitution as let x squared negative 1 be equal to some t. Now differentiating both sides, we get, so this is going to be 2 times x with the differential operator, because differentiation of 1 is 0, and this would give me dt. Now I just only have x there, so I can rewrite this as x times dx is equal to dt over 2. So I would be clubbing this with this. So this is equal to integral square root of 2 times sine x squared negative 1 is t negative sine 2 times t over 2 times sine t positive sine 2t times x dx is dt over 2. I can place the 2 here. Now this is equal to 1 over 2 times integral square root of 2 times sine t. Sine 2t is 2 times sine t cos t over 2 times sine t positive 2 times sine t cos t times dt. This is equal to 1 over 2 times integral root of, I can take 2 times sine t out, and that would give me 1 negative cos t divided by 2 times sine t out. That's going to be 1 positive cos t times dt. 2 times sine t can be cancelled. That in turn would give me 1 over 2 times integral square root of 1 negative cos t over 1 positive cos t times dt. This is equal to 1 over 2 times integral root of 1 negative cos t is 2 times sine squared t, and you have to have that 2 there divided by 2, and this is divided by root of 1 positive cos t is going to be 2 times cos squared t over 2. Right now, of course, we can get rid of this root of 2 over here and 2 over here, and this is equal to 1 over 2 times integral. Now square root of sine square t over 2, which is sine t over 2, square root of cos square t over 2 is cos t over 2, sine t over 2 over cos t over 2 would give me tan t over 2 times dt. Right? Now what is the, now if in case you're not happy with t over 2, you can make the substitution. Now you can directly integrate this. Since we know that integral tan x dx is ln of secant x positive c, you can use this formula here, but you got t over 2 here, so you need to be careful. So this is going to be 1 over 2 ln of secant t over 2. The coefficient of t is 1 over 2, so we divide by that 1 over 2. This is equal to, if you were to flip it, you get 1 over 2 times 2 times ln of secant t over 2. This is what you're getting. But I can cancel these things, but my t is x squared negative 1. So I substitute that, and of course there is a 2 there, so this is the solution to the question. Students were given this question: integral sine squared x cos squared x over sine raised to the power of 5x positive cos raised to the power of 3x times sine squared x positive sine cubed x times cos squared x positive cos raised to the power of 5x, and this entire component is raised to the power of 2. Now you can see that this entire question is a bit huge. So what we do is, instead of simply writing sine squared x and cos squared x, we are going to have some representation. So whenever I see sine, I will replace it by s. So this is going to be s squared, and cos is going to be c, and this is going to be c squared, divided by s raised to the power of 5 positive c raised to the power of 3 s squared positive s raised to the power of 3 c squared positive c raised to the power of 5, and this entire quantity is raised to the power of 2 times dx. Now what I wish to do is, I would like to make some changes. The changes is that I would like to divide this entire quantity by c raised to the power of 5. Now I'm going to do the division inside the parenthesis. So that will mean I would have to multiply it by c raised to the power of 10, because c raised to the power of 5 is inside and that is raised to the power of 2, and to neutralize it I need to have c raised to the power of 10 outside. So that's well understood, right? So now what I will do is I will use the property of algebra, which is if I were to have a positive b over c, I can rewrite it as a over c positive b over c. So by this algebraic property I can rewrite this as integral s squared c squared. Now this can be pushed, this is actually c raised to the power of 10, right, and it is actually resting over 1. So if I were to flip it, this is going to be c raised to the power of 10, and that is divided by, as I mentioned to you, I will be dividing every term by c raised to the power of 5. So this is going to be s over raised to the power of 5 over c raised to the power of 5 positive c cubed s squared divided by c raised to the power of 5 positive s cubed c squared divided by c raised to the power of 5 positive c raised to the power of 5 divided by c raised to the power of 5. This is entirely raised to the power of 2. Of course I've got dx that has to be placed here. So this is equal to, now I'm going to split the c raised to the power of 10 as s squared over c squared, that's one term, and then c squared over c squared, that's another term. So I got 3 more c squared, so it's going to be 1 over c squared times 1 over c squared times 1 over c squared, that is divided by s over c, that's nothing but tan, right? Now instead of writing tan I should have written it as t, so I need to strike that a off. So this is t raised to the power of 5 positive, now this is c cubed and c raised to the power of 5, so that means I would get s squared over c squared, so that would mean this is t squared positive. Now this is c squared and you got c raised to the power of 5, so that would mean I get a c cubed here and s cubed over c cubed, that will be t cubed positive. This is going to be c raised to the power of 5 over c raised to the power of 5, both would get cancelled giving me 1, and that has to be raised to the power of 2, and we got the differential operator dx, right? So we need to do some alterations like that. Now let us replace s squared over c squared as t squared. Of course this c squared and c squared in the numerator will be cancelled. So in the numerator I got t squared times, now what is 1 over cos x? 1 over cos x is nothing but secant x. So 1 over cos squared x is going to be secant squared x, right? But we got a formula, secant squared x negative tan squared x is equal to 1, so that would mean secant squared x is equal to 1 plus tan squared x, right? So you got 1 positive tan squared x here and 1 positive tan squared x over here. So I can write it like this, so 1 positive t squared times 1 positive t squared and 1 over c squared, that's secant squared, so it's going to be secant squared x. I don't want to place it as s, because if I were to place it as s it would mean sine, so I'm just writing it as secant squared x. So now in the, let me first write the denominator. This is t raised to the power of 5 positive t squared positive t raised to the power of 3 positive 1, this is raised to the power of 2, okay, and you got this operator dx, that's fine. Now consider the denominator, t raised to the power of 5 positive t squared positive t raised to the power of 3 positive 1.
Now if I were to take t squared out, this would give me t raised to the power of 3 positive 1, and you've got t raised to the power of 3 positive 1. I can take t raised to the power of 3 positive 1 out, and that would give me t squared positive 1. So I can write t raised to the power of 5 positive t squared positive t raised to the power of 3 positive 1 as t cubed positive 1 times t squared positive 1, right? So this is equal to integral t squared times 1 positive t squared times 1 positive t squared. That's going to be 1 positive t squared raised to the power of 2 times secant squared x divided by, this is going to be, I'm going to write this, t cubed positive 1 times t squared positive 1. This entire thing is raised to the power of 2. Of course, we got the differential operator dx. So this is equal to t squared times 1 positive t squared raised to the power of 2 times secant squared x. Now I'm going to rewrite this as 1 positive t squared raised to the power of 2 times 1 positive t cubed raised to the power of 2 times dx. Now 1 positive t squared raised to the power of 2 and 1 positive t squared raised to the power of 2 can be cancelled. So this is equal to integral t squared times secant squared x divided by 1 positive t cubed raised to the power of 2 times dx. Now I can rewrite this now as tan squared x secant squared x dx divided by 1 positive tan cubed x raised to the power of 2. Now let us make this substitution. Let tan x be equal to t. When I differentiate this, I get secant squared x dx is equal to dt. So this is equal to integral t squared secant squared x dx, that's going to be dt. This is going to be 1 positive t cubed raised to the power of 2. Now this is the substitution t, right? But this is the representation for tan. So if you're not happy with this, you can change it to some other variable. So this is what we have got. Now I'm going to make another substitution. From this I'm going to make another substitution. So let 1 positive t cubed be equal to sum p. I differentiate this, I get 3 times t squared times dt is equal to dp. So from here t squared dt is equal to dp over 3. So this is equal to, in place of t squared dt, I'm going to substitute dp over 3 divided by, in place of 1 positive t cubed, I'm going to substitute p squared. It's actually p because of the degree 2. This is going to be p squared. So I move to the numerator. So if I move to the numerator, it will be p raised to the power of negative 2 dp. I integrate this. If I were to integrate this, this is going to be p raised to the power of negative 2 positive 1, negative 2 positive 1, which is 1 over 3 times p raised to the power of negative 1 divided by negative 1. I can push it down. It's going to be negative 1 over 3 times p. But my p is 1 positive t cubed, which is equal to negative 1 over 3 times 1 positive, but my t is tan x, so it's going to be tan cubed x, and we need to place the arbitrary constant c. So this is a beautiful question, students, and we have achieved the result, and hence this is a good place for us to draw the red line.